So let's take a look at an example. Let's say that I have a function f of xy given by y squared minus x plus 10. And let's say that I have a constraint function given by g of xy equals x squared plus y squared equals 4. So based on the analogy of our previous example, this function is like our mountain function. This is the function that we want to maximize and minimize. And this function is our constraint function, which was like our road. I can tell that it's our constraint function because it's set exactly equal to a constant. So I have just some level curve that's in the xy plane. That's why I know that it's the constraint function. Really, when we work this out with algebra, it's not going to matter which one is labeled as which. But let's go ahead and use our Lagrange multiplier method. I'm going to find the gradient of my f function, and I'm going to set that equal to lambda times the gradient of my g function. And when I set these equal to each other, I'm going to get a whole system of equations, and we're going to do a bunch of algebra, and then we'll come up with a solution. So first, let's recall, what is the gradient of f? The gradient of f is the partial derivative of f with respect to x in the first component of my vector function, and the partial derivative of f with respect to y in my second component. And so in this case, I find that the partial with respect to x is going to be the derivative with respect to x, which is just -1. And the derivative with respect to y is just going to be 2y. And that's going to be set equal to lambda times the gradient of my constraint function, which in this case is going to be the partial with respect to x, which is 2x, and the partial with respect to y, which is 2y. So I need this vector to be equal to some scalar multiple of this vector. This lambda here is just some scalar multiple. Usually we use Greek letters to mean that it's just some constant value. It's lambda after Lagrange. Anyway, so in order for these two vectors to be equal to one another, it means that the x components of the vector have to be equal, and the y components of the vector also have to be equal. So setting the x components of the vector equal to one another, we get that -1 has to be equal to lambda times 2x. And setting the y components equal to another, we see that 2y has to be equal to lambda times 2y. We have 3 different variables that are unknown and only 2 different equations. So at this point, we actually don't have enough information to be able to solve this. To be able to solve this, we need one more piece of information, and I'll write this piece in green to remind us. Not only does the gradient f have to be equal to lambda times the gradient of g, we also have to have the relationship of the constraint function hold. So I also have to have that x squared plus y squared has to equal 4. And at this point, I have a system of 3 equations and 3 unknowns, and we can go back to whatever algebra skills you want to be able to solve 3 equations and 3 unknowns. There's no tricks or shortcuts. My go-to method is to try to solve one variable in terms of the other and then plug it back in. In this case, there are a couple of things that we can do right away. I see that I'm going to divide 2 from each side of this equation, and I come up with the fact that y is equal to lambda times y. So taking a look at this relationship, if y is equal to lambda times y, that gives me 2 possible outcomes. One, I could divide both sides by y, and I would see that lambda was equal to 1. Dividing both sides by y, I get that lambda is equal to 1. I'm going to write that over here. But, cautionary tale, and this is a cautionary tale that comes up a lot when solving these types of equations. I can only divide both sides by y if y is not equal to 0. This equation is also satisfied if y is equal to 0. So I can divide by y and see that lambda is equal to 1, or I also have the outcome that y could be equal to 0. Right? That's what this information tells me, solving this system of equations. So let's use this information and go back to one of the other equations and see what we get for x. So in this case, if it's the case that lambda is equal to 1, we get the fact that, so I'll do this in cases. Maybe my algebra looks messy. I don't have a lot of space here. But if I let lambda equal to 1, I go back to my first equation and I say that that means that x is going to be equal to -1/2, just solving, right, I subtract. And if lambda is equal to 1 and x is equal to -1/2, I can plug that -1/2 into my constraint function and find out what y is. That means that in this case, -1/2 squared plus y squared equals 4, which means that this becomes +1/4. So this becomes 4 minus 1/4, which is 15/4. And that means that y would be equal to plus or minus square root of 15/4. And that's one possible solution. Another possible solution would be when we take the case 2, that y is equal to 0. What happens when y equals 0? Well, this is actually an easy case. We can plug y equals 0 directly into our constraint function, and we'd see that if y equals 0, then x would be equal to plus or minus 2. I can do that in my head by taking the square root of both sides. Plus or minus 2. So notice that all of this work gives us out 4 different solutions. And I'm going to summarize all 4 of those solutions. So in this solution, we got the fact that x was equal to -1/2, and we got 2 different y values out. So I'm going to record these maybe up above here. Can you guys see that? Yeah, I think you guys can see that. So one possible set of solutions is given by x equals -1/2, y equals square root 15. I'm going to say over 2, because that's the square root of 4. Or x equals -1/2 and y equals negative square root 15 over 2. And over here, we also get 2 solutions. These are the solutions when y equals 0. We get x equals +2 and y was equal to 0. And we also get x equals -2 when y was equal to 0. So how are we going to be able to figure out which one are our max and our min values? Because we have this long list of values, but really what we want to know is when are they maximized and when are they minimized? We're going to do one more step by plugging them into our function to find out when they're maximized and minimized. So let's evaluate each of these potential max and min values one by one. So the first one that I'm going to look at is f of -1/2, comma, square root 15 over 2. I'm plugging that into my f function because I want to know how high on the road I am at this particular point. And I notice that I get y squared, which is 15/4, minus -1/2 plus 10, which is equal to 15/4 plus 2/4 plus 40/4, which is 57/4. Did I do that right? That's 40 plus 2 is 42, 52. I think that's correct. Okay. So next I'm going to plug in my next value, which in this case is -1/2, comma, negative square root 15 over 2. And look, I'm going to get out the same exact answer because my y was squared, so it doesn't matter that this is positive or negative. I'm going to get out the negative square root 15 over 2 squared gets me the same thing. So I have a tie for this value. Let's look at our other 2 values. If I look at f of 2, 0, I get out of this function 0 squared minus 2 plus 10, which is equal, minus 2 plus 10, which is equal to 8. And then f of -2, 0 is equal to 0 plus 2 plus 10, which is equal to 12. So notice which values are the highest. 12 is the same thing as 48/4, and 8 is the same thing as 32/4. So I did that to be able to compare that with my 57/4. And I see that these 2 points are our max values. And this point down here, 2, 0, is going to be our min value. And this value is sort of a dud. And it's not that surprising that we come up with duds. Let's analyze graphically what's going on in this situation to give us this behavior.
So I'll label these up here. These two were our max values,
And then at the point 2, 0, that's where we got our min value. So to analyze this,